Hello and welcome to my talk about divide and surrender. This is a joint work with Stefan Gast from Graz University of Technology and Jane Gu, who couldn't attend unfortunately, from Lund University in Sweden, and myself at the Fraunhofer SIT. So divide and surrender, this is about division timing side channel. So we identified a division timing side channel vulnerability in HQC. We developed a new SMT-based exploitation strategy to be able to measure this side channel. We developed a new key recovery method for HQC to be able to recover keys faster. And we evaluated the attack on an AMD Zen 2 CPU. And the final attack runs in less than 2 minutes and can recover the full key. HQC, or Hamming Quasi-Cyclic, is a round 4 contender in the NIST post-quantum effort for standardization of post-quantum primitives. Currently, there's one main selected algorithm, which is Kyber. Kyber is lattice-based, and NIST is looking for alternative candidates that are based on different hardness assumptions. And of the remaining candidates, so Cyc was broken, there's 3 candidates that are code-based, and HQC is one of them. HQC is a key encapsulation mechanism, which means that it has 3 algorithms: a key generation algorithm, an encapsulation algorithm, and a decapsulation algorithm. The key generation algorithm produces a public-private key pair. The encapsulation algorithm produces a ciphertext and a key K0. And the decapsulation algorithm, given the secret key and the ciphertext, produces a key K1. And hopefully, if your scheme is correct, then these 2 keys are equal. And let's look into HQC in depth. HQC generates keys the following way. Everything here effectively operates in this ring R, which is a polynomial ring, but we could effectively view it as bit vectors of length n. The first step that we do is we generate 2 low-weight vectors, x and y, and these form our secret key. Then we generate this polynomial h, which is part of a parity check matrix of a quasi-cyclic code that HQC bases its security on. And we use H to compute the syndrome of the secret key under this parity check matrix. And this syndrome, together with the parity check matrix, form our public key. Now, to encrypt a message in this scheme, we sample 3 random low-weight vectors, E, R1, and R2, compute the syndrome of R1 and R2, which forms part of our ciphertext. Now, we encode the message that we want to encrypt with some public code C that is known, and hide this encoding using noise related to the public key. And to decrypt, we compute V minus U times Y, so V and U are from the ciphertext and Y as part of the secret, and put this into the decoder. Now, the decoder will be successful if there's few enough errors, and this expression V minus U times Y reduces to this encoding of the message M plus some sparse vector, because all of the components in this expression are sparse. The entire expression will still be fairly sparse, and there's relatively few errors that the decoder will need to correct. Now, we have a public key encryption system, but really we wanted a key encapsulation mechanism. So what we use is a variant of the Fujisaki-Okamoto transform to obtain a CCA secure KEM. And essentially, we still run this encryption algorithm, but now we use a random message as an input. And we de-randomize the encryption. So we compute a Z theta that is based on the message M, and then run the encryption using this seed. So all the 3 random vectors that we generated in the encryption functions are now based on that Z theta. Now during decapsulation, we decrypt the ciphertext, recompute the Z theta, and then recompute the ciphertext, and compare this ciphertext to the original ciphertext that we got. And only if these 2 ciphertexts, the recomputed ciphertext and the original ciphertext match, then we output the key, otherwise we output a decoy key. Now, in a previous paper, we found a timing vulnerability in this encryption function, which uses a rejection sampling algorithm to sample these low-weight vectors. Now, usually rejection sampling in an encryption function can be fine because the encryption function doesn't get any secret. But in this case, the secret is the seed itself, because the seed is based on the message, and the message is secret. So this allows us to build a distinguisher, and based on that, we can break the system. Now, that was a previous paper. And the authors of the scheme fixed this vulnerability. Well, supposedly. They implemented a constant time algorithm invented by Nicolas Sindrier, but this algorithm uses modulo reductions. And here you can see a snippet of the code, of the updated code. Here we have 32-bit integers that are reduced modulo some constants. So these are constant known at compile time. And in principle, the compiler has the ability to convert these divisions into, or these modulo reductions into constant time code using, for example, Barrett reductions. But in this case, because of this loop, it does not do so. And instead, it generates division instructions. And we tested some microarchitectures, some high-performance microarchitectures, and these division instructions take a variable amount of time on some of them, at least on Zen 2 and Zen+. So here you can see the numerator of the division, and then the number of cycles it takes. So for each additional bit set in the numerator for this particular divisor, we get one additional cycle that the division takes. Now this already should allow us to distinguish ciphertext, but unfortunately, when we measured this in the real world, we were not able to find this timing difference when measuring the entire crypto system. So only in this lab environment where we are only measuring divisions, we can find the difference, but when measuring the entire decapsulation, we no longer see the difference. So we came up with this new methodology, which we call div-SMT, which is based on simultaneous multithreading, or hyperthreading as Intel calls it, where we are assuming that we are running co-located to the attacker, co-located to the victim that's running the decapsulation algorithm. The victim is running these divisions, and we are also running divisions. And our divisions are competing with the victim's divisions because we are running on shared hardware. So here we are running on the same physical core, running divisions on the same execution engine, and therefore if the victim is running divisions that take a variable amount of time, our divisions will also take a different amount of time. So through that, we can, one, detect whether the victim is running divisions, and two, measure how long these divisions take. And this allows us to distinguish fast ciphertext and slow ciphertext. So a fast ciphertext is one where we brute forced a message so that the numerators that are generated are lower, so the divisions are faster. Now this distinguishing two ciphertexts is already a theoretical break of the crypto system, but really we want the secret key. So what we can do, and this is also from previous work already, is we can craft ciphertexts such that the error that the decoder here has to correct is just Y, and Y is part of the secret key and everything that we need to decrypt messages. And now we can apply an attack from 1999 from Schneier et al., where imagine if this bubble here is all decoding to the fast message, and this other bubble is some random message. And so we can distinguish these two messages through the side channel. And now we start here with some ciphertext plus Y, which is the secret key. Now we effectively take something like a random walk until we notice this transition to this other message. And then we can flip bits back to test if they are part of an error in the ciphertext. Now this attack is quite slow, but it works. But we can perform several optimizations on it. The first thing is to exploit the structure of the code that HQC uses. HQC uses a concatenated code that consists of a Reed-Solomon code and a Reed-Muller code that's repeated several times. And what we can do, so currently we are attacking this entire code word at once. Instead, we can corrupt part of the Reed-Solomon code words such that one more block corruption will corrupt the entire word. And so then we can attack this one repeated Reed-Muller code word. And this tremendously speeds up the attack and is used in the rest of the literature already. Then we introduced this idea of a zero tester, where we can test entire blocks of 384 bits at once and check if all of the bits in that block are zero. And this we do by offline computing an error that when added to the ciphertext will bring us almost to the decoding boundary, but not quite. So any additional errors introduced by the secret key will bring us above the decoding boundary, and we will notice that it's not a zero block, as we call it. So we can test an entire block if it's all zeros, but that's not enough, because there's only 56 blocks. So what we also need to be able to do is to shift the secret key underneath the block that we're testing, and this is also possible. So illustrating this, imagine this is part of the secret key, and we're shifting a 3-bit block and testing if all of the bits are zero. In the first case here, it does not work out because there's a 1 bit there. Here it works out, so we recover all of these 0 bits. And in the other cases, it does not work out. So there's already 2 questions arising here. How do we choose good shifts to recover as many 0 bits as possible with as few queries as necessary? And how do we even get the entire secret key? Because right now we're getting only some zeros. And I will only answer one of these questions in this talk, which is how to recover the full key. It's through this linear relation between the public key and the private key. So X and Y are, again, part of the secret key, and H and S are public. We can only recover half of X and Y, and then recover all of X and Y through this relation, because we already know H and S. So we implemented this attack and evaluated it, and achieved an 8-fold reduction from previous work, and have a success rate of about 78%. Now, to fix this vulnerability, you can either manually implement these Barrett reductions or use a different method to map to the required range. Thank you.